Right, folks. Now we're going to dive into solving some numericals for these, for kinetic theory of kinetic theory of gases. Problem 1. Find the kinetic energy of 8 grams of methane at 20% degrees Celsius. We know that kinetic energy formula for 1 mole is 3/2 kT. Then kinetic energy for n moles is 3/2 kT times n. We know the gas is methane, which is CH4, and to compute the number of moles, we have mass by molar mass, which is C molar mass is 12, H would be 416, and the given mass is 8/16, which would be 1/2. So 3 times K times 1/2 times temperature plus what's the temperature? 27, which is in kelvins. So 3/2 times 0.5 times 300 times K. This will be your answer for the problem. Now we dive in problem 2. Find kinetic energy of 1 molecule of oxygen gas at 127 degrees Celsius. Again, the way that we solve over here for kinetic energy for n moles and 1 mole, we have to do it for kinetic energy for 1 molecule. So kinetic energy for 1 molecule would be 3/2 kT. I think, wait a minute, I have done an error over here. It should be 3/2 RT, because for 1 mole it's 3/2 RT, for 1 molecule it's 3/2 kT, and K is Boltzmann constant, and R is gas constant. So it would be 3/2 times 0.5 times 300 times 8.314 over here, and here we will have for 1 molecule 3/2 times K times since it's for 1 mole of oxygen gas, and T would be plus 127 Kelvin, which is in this case for 1 mole of gas, and as we know by the postulate that kinetic energy depends only on absolute temperature, that's why we know that we don't need anything else, and we don't have to compute the mass and molar mass in this scenario. And whatever we get from this equation, which would be 3 times 1.38 into 10 to the power minus 23 plus times 273 plus 127, which would be 373, 400 Kelvin. This would be our answer. Now, in this problem, if we have, like, say, 3 molecules instead of 1 molecule, then kinetic energy for 3 molecules would be 3 by 2 times 3 times da da da. And this would be the way you are supposed to solve the problem for molecules, and the above one would be for the moles. Now we're gonna find, let me change the color first. Now what we're going to compute is the change in kinetic energy types of problem. For example, problem 3, I think, find the change in kinetic energy of 1 mole of ideal gas when temperature changes by 50 degrees Celsius. Now, in this problem, we are supposed to do something similar that we did earlier, and the thing that we need to consider is it's a 1 mole and ideal gas, because if it is not ideal gas, then we can't apply the equations that we have deduced in previous videos. So, to compute the final kinetic energy, we have to subtract from initial minus final, right? So to do so, what we can do is kinetic energy initial will be 3/2 RT, where assuming T is the initial temperature. Then kinetic energy final would be 3 by 2 or T plus 50, right? Then change in kinetic energy would be KE final minus KE initial, which would be 3/2 or T plus 50 minus T. TT gets cancelled out, then 3/2 R 50. This will be our final answer. Another kind of problem that could be possible with these kinds of problem would be, say, at what temperature the kinetic energy will be half or doubled or 1/3 of its value at given temperature. So to do that problem, what we can do is we can just write a problem at what temperature, let's say the kinetic energy would be half of value at 127 degrees Celsius. So kinetic energy, say at 127, is N times 3 by 2 times R times 127 would be 400 Kelvin, right? Then the problem asks about what temperature kinetic energy would be half of value at 127 degrees Celsius. So kinetic energy half would be kinetic energy at 127 by 2, right? So we assume that the temperature at which the kinetic energy is half would be N times 3 by 2 times R. Say the temperature be T. Then we know from this equation N is 3 by 2 times R times 400 by 2. And if we cancel these things out, then T would be 400 by 2, which is 200 kelvins. So the problem, what the problem was asking is at what temperature the kinetic energy, not the temperature, the kinetic energy would be half of the value at 127 degrees Celsius. So what we computed over here was basically at what value the kinetic energy would be half, and since we know why it is like symmetric to the temperature being halved itself is because kinetic energy is itself dependent on temperature. So kinetic energy 1 by kinetic energy 2 would be T1 by T2. It's because of the postulate that we had earlier in the postulates of kinetic energy. It's because since kinetic energy depends on temperature, it has to be the case that it has to be the case if we halve the kinetic energy or if we halve the temperature, then that would be the required value for kinetic energy or temperature if we have temperature if we have kinetic energy, and kinetic energy being halved would give the value of temperature because of the direct relationship between them. Now let's dive into another problem. Let me check the color, and we will just do the problem. I think I messed up the numbers, but it should be fine. So the problem goes like this. So I'll draw a container, which would be like this. Don't judge my drawing. And we assume that its side length is A, and the gas filled in it is helium gas molecules. And the problem statement would be they make 500 collisions with the wall in each second, which means these helium gas molecules makes like 500 collisions per second. And just to give you an upside, you should know that in postulates we defined our equations in a way, we defined our postulates in a way that there is no intermolecular forces between gas molecules. So the pressure that might be visible in the problem will only come from the collisions with the wall. So don't get confused by the intermolecular forces between helium gases, because it doesn't exist as per our postulates, as per the ideal gas law. And we know, based on this information, we know that helium gas has a mass of 4 grams. Now, find the temperature of gas. It's a very conceptual question, by the way, because we can't just solve this problem by using, say, kinetic energy is equals to 3 by 2 kT, or PV is equals to 1 by 3 mnu RMS square. You can't just use it in this problem. What we have to do is stick to the basics and understand the concept in this problem. I would ask you to feel free and try this problem, because it is not, we can't just do it using these equations, because what we have to do is apply unitary method and find the number of collision in 1 second and 1 collision in how many seconds, then use it all together to solve this problem. I suggest you to pause the video for a while and try solving it on your own, and I hope you paused it and did it. Now I'm going to do this problem. So we know that time for 1 collision is equals to 1 by 500 seconds, right? And how do we define one collision in this container? Usually in this problem of ideal gases, if this is our container, and let me change color, and if this is our molecule, then the time taken for one collision is defined by the fact it collides this way and that way, right, on the both ends. And this is the size of the particle, and you must remember that how the molecules move is in straight lines on axes, ux, uy, uz. That's why we can assume for the fact that it's always traveling in straight lines, right? So the time for one collision is 1 by 500th of a second, and the distance travel is somewhat a, right? The distance travel over here is like a in one direction. So if it travels in both of the direction, then the total distance to make one collision would be to hit here and again back there and then coming to this point back, which is distance traveled for the collision is 2a. I hope you got it, because this is an important aspect of it. Because how we define collision in physics problems is after colliding with some body, since it's an elastic collision, after colliding it with this wall and then again colliding back to the other wall, and then coming to the initial position after coming to the initial position, the total distance traveled would be the distance traveled for the collision, and the time would be the time for collision. So the distance has to be 2a, not 1a, because the point can be randomly anywhere in this container, and we have to make sure that we are considering a collision, a proper collision if and only if the point, if the molecule or if the gas particle comes back to its original position after colliding with the walls on both ends in straight line, because the collision that we have assumed is straight lines. So it has to be 2a. Right? Now, URMS in this case would be distance by time, right? Then 2a would be 1 by 2a, 1 by 500, which is 1 by 500 if we send things, if we move things around by doing some algebraic calculation, then URMS would be 2a times 500, assuming a is equals to, say, 2 centimeters in this problem, then times 0.02 times 500, right? And we'll have the value of URMS, which is 1000 times 0.02, which is 2 times 10 to the power minus 2 zeros and 10 to the power 1 meters per second, which is 20 meters per second. Now, since we know URMS velocity for one molecule in this problem, then the thing that we had to compute in this problem was find the temperature of the gas, right? So kinetic energy of, now what we can do is basically use these equations to compute kinetic energy of one molecule, then use it alongside with other two equations to compute kinetic energy, and by those equations we can compute the temperature. It's a bit of a mouthful. I can show you what we will be doing next. Is kinetic energy of one molecule is 1 by 2 m(u(rms) squared, right? And we also know that kinetic energy of one molecule is 3/2 kT, right? Which is again kinetic energy of one molecule, right? So now, since we know URMS, the value of K, m, 1/2, 3/2, then what we can do is equating equation 1 and 2, we will have 1 by 2 m(u(rms) squared is equals to 3/2 kT. We know the mass of this molecule, the gas helium, is 4 grams, because helium's atomic number is 2, and we are supposed to multiply it by 2 to get the value to get the mass of the helium molecule, which should be 4 grams, and the equation would be 1/2 times 4 times 10 to the power minus 3. It's in kilograms because SI unit, of course, times 3/2 times K times T. 2 gets cancelled out. 4 times 10 to the power minus 3. URMS is 20 squared, 3 kT. Then T would be 4 times 10 to the power minus 3 times 400 by 3K. Now, if we just plug in the value, then what we're going to get is a value in Kelvin, which would be temperature that we're supposed to compute in this problem. It was kind of a tough problem, if you ask me, but it's a conceptual one, and I'd love you to go through it again if you're confused. And if you can solve this problem, then you can basically, if you know how to solve this problem, then I would assume that you know how the postulates work in this problem. Again, to reiterate, if I have to, then the postulates that has been displayed in this problem, or that has been tackled in it, was, since the collision is since we have collision with the wall, it strips away the collision intermolecular forces between those molecules, so that we don't have to consider those collisions, which is the postulate of the problem. And with the given postulate, and given the fact that we are computing for one molecule, what we did was we computed URMS, which is velocity is equal to distance by time, and using that equation, the URMS value is 20 meters per second, and a general kinetic energy formula would be 1/2 mv squared. Using that equation and the equation that we derived in this problem, in this module, for one molecule, which is 3/2 kT, if we equate both those equations, then we can easily compute temperature in this problem. So I think this is the last problem in this module. Now, after this, we'll be continuing this module, and we will talk about more difficult concepts in kinetic theory of gases, and we'll be doing more problems in it. Thank you.